This episode is supported by the Great Courses Plus. One of the most enigmatic of all astrophysical phenomena is the mighty quasar. They're also a subject of my own research and so are close to my heart. Let's talk about what happens when the largest black holes in the universe start to feed. Space stuff is awesome. Take stars. 100 billion megaton per second thermonuclear explosions that just don't stop exploding. Pulsars, city-sized atoms that beam death rays through the galaxy. Giant molecular clouds, beautiful and tranquil, but also screaming vortices spitting stars into the cosmos. Of course, everyone knows that quasars are the most awesome of all. They have everything. They're like the fire-breathing, bat-winged vampire rainbow zebra unicorns of astrophysical phenomena. They don't just have a black hole, they have a supermassive black hole, millions to billions of times the mass of the Sun. That's surrounded by a solar system-sized whirlpool of superheated plasma that shines brighter than an entire galaxy. Sometimes they even have jets of near-light-speed particles filling the surrounding universe with giant radio plumes. Yep, quasars are clearly the most metal of all the space things. This is one reason why I study them myself, but it's not just that they're cool. Quasars helped shape our universe. In fact, without these most violent of all astrophysical phenomena, we might not be here to think about them. Let me start with a bit of history. When the very first radio telescopes pointed to the heavens, they saw fat blobs of radio light whose sources were unknown. Those blobs were only blobby because those early radio antennae had some pretty bad spatial resolution, making it difficult to pinpoint exactly where on the sky they were located. Then, in 1962, astronomers caught a break. In an event known as an occultation, the moon passed right in front of one of the brightest of these radio blobs. It was object number 273 in the brand new 3rd Cambridge Radio Catalogue, 3C273 for short. The Parkes Radio Telescope in Australia was trained on the occultation and registered the exact instant that the radio signal vanished behind the moon. That timing allowed astronomers to identify a tiny star-like point of bluish light as the source of the radio emission. Astronomers turned their optical telescopes on this strange star and split the light into a spectrum. It looked nothing like the spectrum of any star ever seen, and so the name quasi-stellar radio source was born, later to become quasar. But what was so different? For one thing, its spectrum was redshifted. The wavelength of its light stretched out as those photons travelled through the expanding universe. That put 3C273 very far away. Its light must have been travelling from 2 billion light years away to acquire the observed redshift. Yet to be as bright as it appeared at that distance, the weird object had to be emitting many galaxies worth of light from a seemingly impossibly small region of space. A hysterical flurry of hypothesizing followed. Swarms of neutron stars, an alien civilization harnessing their entire galaxy's power, bright, fast-moving objects being ejected by our own galaxy's core. But by the 1980s, we were converging on the most awesome explanation. It goes a little like this. Take a black hole of millions to billions of times the mass of the Sun. Where from? Well, it turns out that every decent-sized galaxy has one at its core. Now, drive gas into the galactic core. One way this can happen is when galaxies merge and grow. That gas descends into the waiting black hole's gravitational well and gains incredible speed on the way. It is swept up into a raging whirlpool around the black hole that we call an accretion disk, where its energy of motion is turned into heat. The heat glow of the accretion disk is so bright that we can see quasars to the ends of the universe. Some gas is swallowed, causing the black hole to grow. However, a lot of it never makes it below the event horizon. Some is converted directly into energy and radiated as light, and this same light drives powerful winds of gas back out into the surrounding galaxy. In some cases, for reasons we don't fully understand, some of that gas can also be swept up and collimated, channeled into jets that erupt from the poles of the quasar. This may be due to the magnetic field of a rapidly rotating black hole, but the jury is still out. The exact appearance of this phenomenon depends enormously on our viewing angle. Looking down onto a bright accretion disk, we see a quasar in all of its glory. But viewed side on, that disk is obscured by a thick ring of dusty gas. Then, we only see hints of the central monster because it lights up gas in the surrounding galaxy. However, if such an edge-on quasar has powerful jets, we see them blasting through the galaxy and even filling intergalactic space with beautiful radio plumes. We call these radio